Hey, good evening. Can you hear me? Just we're waiting some time, then we'll start, okay, for joining all of other participants. Can you hear me?
Hi, yes, yes.
Just we're waiting some time, then we'll start. Okay.
Okay.
So basically for the Ramadan, very tight schedule.
Oh, okay.
So
So you talk about the river threshold 1000. What is that 1000?
it's a river network.
So what should be the threshold? It should be 1000?
For the river, mainly we find out that 1000 is better for the river network.
Mm-hmm.
For the
If you
river,
if you if you if you put less than 1000, what happened?
then it also also filter some river network.
But
It
but
also
not all the rivers.
yes, not including
Mhm.
all the river.
Okay.
So, but maximum time, it should more better or perfect result. When you set the threshold value 1000, then it looks more, we can
Mm.
easily check all of river network.
Okay.
So let's go start. After completing the 3 hours live training, then talk about the problem solving class. Okay. Basically today, fourth number class. Okay. And fourth number class, we discuss about the some advanced topic on GIS and remote sensing using the Google Earth engine. Okay. So let me share my screen. Can you see my screen? Is it visible? Let's go. So basically today's session I discuss about that how to remove and how to remove cloud and haze from your satellite imagery. Okay. So in the satellite imagery, we find out the lot of cloud and lot of haze. So this type of cloud and haze also hampered our images. So that's why it is also very important to get the neat and clean satellite imagery all time. So we also discuss about that how to remove how to remove cloud and haze from our satellite imagery. It can be Landsat or Sentinel, both of imagery we try to discuss, and also discuss about the DEM data, basically digital elevation model, how to use the DEM data and create the different types of topographical mapping, such as hill shaded map or slope map or aspect map. So how to create, and also discuss about that LST, mainly land surface temperature monitoring using Landsat satellite data. Okay, so MODIS satellite data we already discussed about that, how to use MODIS LST or MODIS land surface temperature. So today we discuss about the Landsat satellite imagery. Okay, how to monitor LST, mainly land surface temperature, and this LST also connect with urban heat island, how to identify urban heat island, and urban heat island it also connect with urban thermal field variance index, many urban heat island we also discuss, and also discuss about that urban thermal field variance index. Okay, so these two topic we also discuss after discussing LST using Landsat satellite data, and how to calculate average, maximum, minimum NDVI for any specific region also discuss, and how to make the monthly evapotranspiration times recharge we also discuss about that. Okay, so one by one we discuss about the roll up topic. So let's go. So first of all, we discuss about the LST because it's very important. LST. If you simply search some paper, suppose let me show you that from Google Scholar. Just stay open. And so this is the one kind of paper assessing and predicting land use and cover, and also land surface temperature and urban thermal field variance index using Landsat imagery for Dhaka metropolitan area, as well as if you check this is the another one, modeling the impact of land use land cover pattern on urban thermal characteristics in Kuwait. And if you check also this is the another, I hope you don't use the LST exposure of urban green space and mental health during COVID-19 pandemic. Okay, as well as it also use the old fires. So this type of paper, we also try to use the LST, okay, using Landsat satellite data. So let me one paper just open. Suppose this is the paper. It also discuss about that mainly seasonal land use and cover for different season, and it also work with the land use land cover classification, water bodies, urban area, vegetation, bare land. It also try to classify it using machine learning in Google Earth Engine. And for today, discuss about that LST. Okay, land use land cover. Discuss about the further class, inshallah. So today discuss about the LST estimation of LST using Landsat data, and also urban heat island, and also discuss about the urban thermal field variance index. So if you check, maximum all of algorithm similar, not much any difference. Almost all of algorithm has a similar formula. So this type of formula, LST equal to TI. TI basically the surface temperature or represent the sensor brightness temperature. Sensor brightness temperature. Then if you check the it's a lambda, the constant value. Then if you check the TI, or TI is same sensor brightness temperature. Then emissivity, it's a emissivity. We need to calculate the emissivity also. So this is the formula. We can easily compute it all of those using Landsat data. And we also compute the UTFVI, urban thermal field variance index. So for that we need to use formula. It's a formula for urban heat island, the LST minus average LST divided by standard deviation of LST, then we can easily get that urban heat island, as well as urban thermal field variance index. So this formula is equal LST minus average LST divided by LST. Then we can easily get the urban thermal field variance index. So now how we work this type of algorithm, we discuss about that. Not only for that, if you check other paper, so let me show you that. Simply search suppose LST using in Landsat imagery. Really find out a lot of algorithm, a lot of paper, or a lot of method. Suppose let me show you some image or algorithm. Let's search here. Suppose if you check this type of paper, this is the algorithm about that. Okay, let me show you the paper. Just I open. So this is the contribution of Landsat 8 data for the monitoring the LST using Landsat data. So this is the follow chart of this work. So first of all, they are take the band 10. Band 10 basically thermal infrared band. Band 5 is the near infrared band. Band 4 is the red band. Okay. So simply computed NDVI using two band, and after that compute the vegetation proportion. Then use the brightness temperature and also vegetation proportion, compute the surface emissivity. So after computing the surface emissivity, then just apply the monoid algorithm and compute the LST or land surface temperature for this city. Okay. And they are also compare the MODIS LST data and Landsat LST data, find out the correlation, mainly R square value correlation. They find out that high positive correlation and also computed the y equal to mx plus c, okay, linear equation. So let's go try to discuss about that, how to apply this type of algorithm. So first of all, we need the Landsat data. So let's go. Let's open a code editor, or just I write the code in here. Okay, so let's go. So first of all, you need to import your area. Okay, suppose we is area you want to enter, the LST. So now we discuss about that. We already know, we compute the MODIS. Okay, MODIS LST. We already know about that. Okay, MODIS LST. So MODIS LST and Landsat LST. What is the difference between two LST? Okay. So MODIS, this resolution when you computed it, this resolution it was 1000 meter. Okay, 1000 meter. This resolution, this image resolution, 1000 meter. So when we apply this data for the small study area, suppose a small city, a small boundary, or local region, to check the LST, then it shows some grid or cell. Okay, but this data is perfect for the big study area. Big study area, we can easily work with that big study area or big geospatial area. Okay, big or big geospatial analysis. You can also use the MODIS. There is no problem. Okay, it's a 1000 meter. But when you work with a small study area, we try to choose the high resolution satellite imagery. So for that, we simply apply the 30-meter resolution. Landsat is the 30-meter resolution. So this imagery we can easily apply for a small study, okay, to get more better map. Okay, so that's the region we simply use the Landsat for the small study area to monitor the LST, because a small study area we can easily get the high resolution image for Landsat. But for the MODIS, it's not possible. Okay, for the small study area, MODIS is not possible to get the good quality map, because MODIS resolution is 1000 meter. So it's very work well for the study area or big geospatial analysis or global data analysis. We can easily use the MODIS. But when you work with the local study area or a small study area, then you must use the Landsat data to create more better map. So in this case, suppose I just upload my study area. I'll just be try to upload study area. Suppose just I work for this city. Simply import my district boundary shapefile. Okay, we already know about that how to uh, import the district boundary shapefile. So just I simply import the district boundary. So from this shapefile, I simply choose a specific district in Bangladesh. So I take a variable, suppose RY, then equal I just call the table. This table is stored all of district boundary in Bangladesh. Just I call the table. So this table I want to filter. How I can filter? Art engine dot filter dot equal. What's equal what? Just we get the information from this attribute table. If you check the attribute table from this shapefile, it's a district boundary shapefile. It's including all of districts in Bangladesh. So I just click, okay, just let me click on the features. So in the features, if you check this name too, so this column is stored all of district name. Okay, name two. Just take copy the name two. Paste here. Okay, name two. And now I want to just put my study area. Suppose my study area is Gazipur. Just I put the Gazipur. It's my uh, district name. So now this Gazipur district is stored in this ROI. So I want to add the layer. So just map dot add layer, call the ROI, and also focus on the given study area. Just use map dot center object. Object is ROI. I put the zoom level suppose 10 and run the code. So now it show you your study area. Suppose this is my study area. So for this district, I want to monitor LST, urban heat island, and urban thermal field variance index for the present time. But if you check this paper, so in this paper, we simply just show the different decades, okay, different decades and seasonal, suppose summer season and rainy season. We also try to compare. We also try to compare summer season or rainy season, okay, for the comparing LST data. And you can see it take the winter, summer for the two season. That use the Landsat 8 data for this 2020 15 April that use this data, and also take this data to 2000. So just it creates some compare. The same way, same process. So let's go try to take the imagery. So now we simply take the imagery. So for the imagery, just click on the browse data catalog. Then we can easily access all of imagery from Landsat, Landsat 2, Landsat 9, Landsat 8. We can see Landsat 9, Landsat 8, Landsat 7, okay, Landsat 5, Landsat 4, Landsat 1 to 5. So all of collection. So I want to monitor present time condition, present time. Suppose 2026, this time I want to monitor the LST. So for that, I just click on the Landsat 9 again and click on the surface reflectance. I am not using proper atmosphere because I want to monitor land surface temperature. So that's why I just simply use the surface reflectance data. Monitor land surface temperature. Just click on here. So now it gives me all of information. We already know about that how to filter the image collection. I already discussed in the second number class how to filter the Landsat image collection, Sentinel-2 image collection. Okay, so same way. Just we copy the snippet ID from here. Just I copy, paste in our code editor. Just I paste. Then give a variable name. You can put any name. I put the name suppose. You can put any name. I put the name suppose L9 and equal. So you can put any variable name, this type of variable. And this is my image collection. I simply use and use this variable. So now this image collection is stored in this variable. So this image collection further I need to filter. Okay. So previous class we already discussed about the sum function, one function for filter bounds function. Okay, with ROI. Second function it's called the filter metadata function. Okay, so filtering cloud cover operator less than. I said the value was one, and when I need the image, just put the filter date. When you need the image, suppose I need the image in 2026, 1st January. So it's present time. Present time. If you check the last time period of the image, the 26th, 11th March. Okay, 0311. Let's just type input this time. 2026 March 11. So just I use the present condition, but you can put any time period. Okay, any season, any time period you can just include, no problem. So now I just try to print how many images in my collection, how many images stored in my collection. I want to check it. Just if you check, it's computing two images available for this time, and this two image is less than 1% cloud cover, and this two image is overlay with my study area of Gazipur boundary. So now I want all of image and create the median composite and then clip with my study area. If you want, you can also scale that image. Okay, previous classes I discussed about that how to take single date imagery. So in this step, I just create the composite, image composite, and clip with my study area. And I want to visualize map.add layer, call the L9 to just add the layer of my imagery. So now it's adding this type of imagery without visualization. Find out type of imagery. So you find out this type of imagery look like that. And I want to add, the visualization parameter. Just I click. Now I add the red, green, and blue, and further custom stressing at 98%. So I find out this type of imagery. Just I import and copy the visualization parameter from here and paste after the object name. Put the layer name, suppose it's the imagery. Okay. So I simply take my imagery for my study area. So this is the first step. We simply take our imagery and we find out this type of imagery. Okay, so this imagery looks more pretty, not much cloudy, because we choose less than 1% cloud cover. So now I want to monitor LST. Okay. So for the LST, first of all, I need to compute NDVI, normalized difference vegetation index. Okay? I need to compute NDVI. So if you check, we need to compute the NDVI. So we need to apply this formula near minus red divided by near plus red. So this formula and compute the NDVI. So let's go try to compute the NDVI. To check this paper also, it also compute the NDVI. So maximum all of paper is a similar uh, algorithm. So we need to compute the NDVI using this using this two band. So let's go try to compute the NDVI. We'll learn about that how to compute NDVI or any other indices. So just to take a variable, suppose NDVI, and then we apply different method. Suppose I just apply this method call L9, or just simply apply different method. We'll learn about that. Suppose I just apply the normalized difference function. Okay. So just I call the L9 and apply normalized difference function between two band. Then
Excuse
infrared.
me.
Yeah, please.
Why you are putting L9? Can you put some other one for this one?
It's a
Or
variable. You
you
put
are okay, okay.
it's a variable. We can put any because this imagery is stored in this variable. Okay? This
Okay, okay.
imagery, we can put anything.
Hmm.
Okay, let me just suppose I put the image. It's
No, no,
better.
no.
So
That
okay,
is fine.
okay, no problem.
That is fine. L9 is fine.
Okay. So L9 is it can be anything, no problem. Just I put the normalized. So from this imagery, I want to apply the normalized difference between two band. I just mentioned the band name. Near infrared SRB5 and red. Red is that SRB4. Okay. So now I just simply add the layer. So map.add layer and call the NDVI and run the code. So now it's added the NDVI layer, look like that. If you want, you can also add the color to visualize the vegetation. Suppose I put the mean put the max, and also add the color plated of vegetation. So we can use different types of color. Suppose I put the blue color, then white color, put the green color, okay? And then mean max value is simply stressing from here and then paste in my code. I was just stressing this data into 90%. I keep, so now it give me this type of value. Just I copy and paste, and also copy. Now run the code. So now this color is set with my map. So we find out to this type of map, okay? Type of vegetation map. So green is indicating about the vegetation. Find out. So now this is my vegetation map. We need to compute the NDVI. So after computing the NDVI, we need to compute some others. So if you check the NDVI, you need to compute the vegetation proportion. We need to compute. Okay. So what is the vegetation proportion? If you check the vegetation proportion, have a formula. If you take the formula, where is the formula? Let me show you that. So this is the formula. PV mainly represent the vegetation proportion. So this formula is NDVI minus NDVI minimum value divided by NDVI maximum value minus NDVI minimum and power 2. So this formula, when I compute it, I need the two value, NDVI minimum value and NDVI maximum value. Okay. Then I need to apply this equation. So, okay, let's go try to compute. This is my NDVI map. So now from here, I compute the maximum and minimum value of NDVI. So just I take a variable, suppose max, and call the NDVI. So from this NDVI, I want to compute the maximum value of NDVI. Okay. So just I put the reduce region function to compute statistical value for my from my NDVI map. In this case, I want to compute maximum. I want to compute maximum NDVI value. So just I put all of our argument one by one. So just I make a dictionary, curly bracket start and curly bracket end. So first of all, reducer. So I want to compute maximum value. So put here EE dot reducer dot max. So it computed maximum value. Geometry, it's your shapefile variable name, which is RY. Scale is the resolution of your satellite imagery, 30 meter. And others in this time not need. Just I remove all those. It's not need. Just I remove. So now if I print, if you check, just I print this maximum value, just put here the max and run the code. So now it's computed maximum number of NDVI, maximum pixel value of NDVI. You find out. Okay. Just if you check, so this is the value 0.43. It's a maximum value. But if you check, it shows as a dictionary. It shows the dictionary, and dictionary have a keyword and key value. This is the keyword and this is the key value. But I need only this value. Okay, I need only this value. So for that, I apply here values function. So now if I run the code, then I can check it show the list computing as a list. So from the list, I need the first item. 0 refers to the first item. 0 refers to the first item. So I put here that dot get and apply the 0 and run the code. So now it's display the only the value as a computed object. It shows as a value, only value 0.433. But this value I want to use in my equation as a number, as a number. So further we simply define ee dot number bracket start and close the bracket. So now if I run the code, if you check, it show the result number computing. So now this value work as a number data type, number data type. So this number data type further I can easily apply any other equation. Same process you also apply to compute minimum value of NDVI. So just I copy same line of code And then I simply change the variable name, suppose mean. Also put at the mean, and I want to print this mean. And now run the code. So now you easily find out that minimum value of NDVI. So now we can get the two value, minimum and maximum value of NDVI for my study area. So for this study, we find out that it's a minimum and it's a maximum. So after getting this minimum and maximum value of NDVI, we can easily apply this formula, mainly PV, NDVI minus NDVI minimum divided by NDVI minus NDVI minimum power 2. So let's go and try to compute this formula, and it's called the proportion of vegetation or fraction of vegetation. So further, I simply take a variable. Suppose I take a variable name is PV. You can put any name. Well, I just apply here. I just call the NDVI, okay, minus subtract with minimum value of NDVI, minimum value mean. Okay. Then I put here that divided maximum value of NDVI. So maximum value of NDVI, then divided, then subtract with minimum value, minimum value, and full equation power 2. So just I cover the equation, use the bracket and close the bracket. Just I make use the cover and put the power 2. And 2 is a number. So when you construct any new number in the server, we need to apply the function AE.number and then define the 2. So now it works as a power 2. We simply apply the equation NDVI minus NDVI minimum value divided by maximum value minus minimum value and power 2. So now further, if you want, you can also just add the layer. So map.add layer of PV and run the code. So it's create the proportion of vegetation layer. So we can get this type of map, proportion of vegetation. If you want, you can also add the color. Okay, it's optional. So now we try to compute brightness temperature. Okay, try to compute brightness temperature. Okay, so for the brightness temperature, if you check the imagery, have a band. It's called the STB10. STB10. It's mainly brightness temperature band, and this unit is Kelvin. Okay, so it's a band 10 surface temperature. We simply use it, this band. So just I copy the band name, take a variable, suppose TI 12. I call my email. Okay, sorry, L9. It's because it's stored on the my image. So I call the L9 and select. So from this L9, I select the band STB10. And now I need to reproject the scale value. So this band have already have the scale value. Just I copy the scale value to, basically it's a digital number. We simply convert into reflectance value. So further we need to apply the scale value and offset value in our imagery. So just I multiply with this scale and also add with the offset value. If you check the offset value, find out this is the offset value. So now if you want, you can also play the brightness temperature band TI and run the code. So now it's work for the TI. We find out that brightness temperature band. And it also called the thermal band also. It's a thermal band or brightness temperature band. Okay. So it look like that. If you just stressing, then you can get the better view. Or if you want, you can also add the color. Just stressing. Apply. Okay, I put the grayscale color, no problem. And import. Type of white color, it show the high brightness temperature. This type of white color, high brightness temperature. And this type of blue black color, it's a low brightness temperature. Suppose this type of blue color, it can be water body. It's a water body with this type of blue color. And this type of white color, it should be your build up construction. Okay, this type of feature absorb lot of heat, mainly concrete or construction, building, build up. So these are roads, so it absorb lot of heat but not release. Okay, so that's why it show this type of place is very high brightness temperature, this type of white color. But for water body, the water body, the water body, so this type of place is not mass brightness temperature.
It absorb or it reflect?
Absorb but not release.
I mean for these structures, bright color means
Step.
it absorb or it reflect more.
It reflect more energy.
Hmm.
Absorb and reflect more energy.
Hmm.
So that's why it show this type of white color. And for water body, the low value type of water body.
That means water body it absorb
And also
or
release
what?
more. Okay.
Low.
Yeah. Because this type of water would or vegetation, but concrete or build up or construction area create this type of white color. But you can see for the water body, so the low brightness temperature. So this type of place is the high brightness temperature type of white color. It's a high brightness temperature, and it's a concrete or build up or settlement type of place also. But for the water body or station, it shows the low brightness temperature value. Okay, so now this is the one. So then we talk about that another parameter. It's called that emissivity. So for the emissivity, take this paper mainly EM or emissivity. So in this case, emissivity of land surface. So basically, estimate the values with their corresponding NDVI values. Okay, so it's not use any formula. It just simply take some previous literature, and further, it just suppose if the NDVI value less than this value, suppose less than 0.185, then they are use 0.995 as the emissivity value. Or if the NDVI value between this range, then use this value. Okay, if the value is the 0.157 or less than equal this value, then use this value. Okay, or if the value NDVI suppose greater than 0.7, okay, then you need to use this value. Okay, this is the value, a spectral emissivity value. But this value we can also compute other equation. Okay, so this equation you can also apply and compute this type of value. Or if you without equation, if you want, suppose if you take in my NDVI this 0.074 and 0.4 and negative 0.07, it at 0.4. So we find out, suppose 0.4, 0.1 less than equal NDVI, and you can see 2 in. So I think we find out this value 0.4. Or if you check the negative value is 0.4 and negative 0.07. 0.07. I think it just this type of range we find out this value 0.157, but it show the but it not maintain the negative. So we try to compute the value. Let's just a minute and then check what happened for the computing the value for emissivity. So EM basically emissivity, and this emissivity have a formula. So this formula is 0.004. Okay, different types of paper already use this type of formula. 0.004 multiply with PV plus 0.986. Okay, so this is the formula. So when you compute the formula, basically we already compute the PV. So when I just use the PV and compute this formula, then we can get the emissivity value or emissivity map. So for that, just take a variable. Suppose I put the variable name is EM and then call the PV multiply the number 0.004, 0.004, and it's a number. We put here EE dot number and define the number 0.004. Okay. So we multiply and also add with another number, EE dot number, and number is 0.986. Okay. We simply compute and then further just add the layers. So map dot add layer, put here the EM. So now run the code. So now it's create the emissivity layer. Like that, let me try stressing and show the result. Find out the value 0.98 to 0.98, this type of range or emissivity 4. Just copy, paste after the object name and run the code. So it generated the emissivity. Now, finally, just apply. If you check our final equation, look like that. Okay. So here, Ti, brightness temperature, we already computed, and logarithm emissivity, we already computed. So Ti and emissivity is already computed, and lambda and rho, this two value is the constant. Okay. If you check the rho equal to this range or this value, we find out that 1.438 10 inverse 2. So it's a raw value. It's a raw value. 1.438 10 inverse 2 is indicate the Planck's constant, which is equal to, okay, so it's a value, this one, and shows the velocity of the light equal to okay, and we find out that one, it's a Boltzmann constant value. So now lambda and rho, so this two thing is the constant. We simply use. So let's go try to apply this formula. So this is the Ti. Okay, so let's go try to apply formula. So take a variable. Suppose I put the variable name is the LST. Well, so now we simply call our thermal band. A thermal band. So just thermal band, basically it's a Ti or brightness temperature. And I apply the expression, put our formula. So first formula is simply apply. Just I put the equation. Suppose Ti, brightness temperature, divided by 1 plus 0.0015 multiply TI divided by 1.438. These things we simply multiply with logarithm log m or emissivity, the em, no problem. So we find out this type of equation, and this equation give you the result as a Kelvin. But when I subtract the value 273.15, it give you the result in degrees Celsius. Okay, so just subtract this value, we can get the result degrees Celsius. Then just put the comma sign, and then so in the equation Ti, it's really basically keyword. So I put the keyword and key value one by one. So Ti is that Ti. This Ti it's just come from this thermal band or brightness temperature. Just a copy and paste. And finally, if you take EM, it's another constant, another variable EM. So this EM just come from emissivity. So this emissivity, we already computed the emissivity. Just I mentioned in here. And I just put the rename as a LST. Just LST. And further, we simply add the layer. Suppose just map dot add layer, all the LST, and run the process. So now it generate the final output of LST. So look like that. Okay, we try to add the color. This is more better. Suppose I put the uh, also put the max, put the color plated. So I put the different types of color: blue, green, yellow. Then suppose red for the high temperature for the red. And min max, I just click on here, tracing, copy, also copy this one also. Now run the code. Okay, we find out this type of place. Okay, it's a high temperature. Okay, so is the low temperature. If you want, you can also check. Suppose click on the Inspector tab and just click this type of place. Find out that it show the temperature 30.25 degrees Celsius. I need to check suppose this type of place blue color. It's a low temperature. So we find out the 21.0 degrees. It says this type of Celsius. We find out. Click on here. So we're at 31.4 degrees Celsius. So this is our final output. Look like that. So here is the high temperature. This type of place red color indicating about the high temperature. And further, we also export this map as a GeoTIFF file format, and then we can easily make the map using QGIS software or ArcGIS Pro software. So inshallah, next class we discuss about that how to create, how to download. You already know about that how to download GeoTIFF. Okay, so this tip will simply work with the
Yeah.
QGIS or ArcGIS Pro to create the more better map. Let's discuss. Yes, any question, please?
Can, can you just export this one?
Yes, yes. At the
Geotree.
yeah,
Can
GeoTIFF.
you
Yes,
write a code?
yeah.
Yeah.
Okay, I'll
Can
show
you
you.
write a code here?
I'll show you that. So we already discussed about this code also. So I will try to show you that again.
Yeah.
So further, we simply write this code. It's called export to try this code. So now put all of those one by one. So just make a dictionary, curly bracket start and curly bracket end, curly bracket start and curly bracket end. And further, you can see the image. Image basically, which layer you want to download. You can see my layer, there are the lot of layer. Okay, so this is the
Yeah.
LST. This is the different types of layer. So which layer I want to download? I want to download suppose layer, this layer, this layer, this map I
Mm,
want to download. Basically layer 7, I want to download. So this layer, this map, store it in a variable. You just find out the variable name. So in this time, this map, it is stored in the LST, this variable. Okay,
mm.
store it.
Yes.
Just I paste here my map I want to. But when I suppose download second one, suppose then this map, which variable is stored, I need to find out and then put the name. Then it will be exported as a geotip. So I need this map. So I find out this map is stored in the LST. I just put the LST for that. Okay. Description, you can put anything as a name. You can put any name. I put the name suppose uh Gajipur. See?
Temperature. Mm,
2026. I'll just put this type of, you can put any name. No. Then folder, we can put any folder name. I put the folder suppose GE. File name previous.net, just I remove. Dimension.net, just remove. Then region, it's your shapefile variable name, which is ROI. Scale is the resolution of your satellite imagery, which is 30 meter. And others,
mm,
if it's not need now, it's optional, just I remove. So now if I run the code, then our task tab will be running. And from this task tab, we can easily download the ST map as a GOT file. So further, we can also use ArcMap or QGIS software to produce our map for the research paper or presentation. The task tab now run.
mm.
So now it is
Then,
starting the downloading.
then another question is, how do you make a legend on the GE? For example, this one, LST legend.
Yes, we also discuss about that. Also, no problem. We also discuss how to add the legend, gradient legend, and also classification legend in GE. We also
Yeah,
discuss. No problem. We also try.
yeah,
No,
yeah, gradual and
I will discuss. No problem. I discuss. So now we generate the LST, but now I want to from the LST we try to compute uh, urban heat island. Okay. So urban island basically it experiences the higher temperature than their rural area. Okay. Suppose rural area, we find out the some trees, some vegetation or water body. So that's why it show the cool condition. But when you work with the urban or build up or settlement, so it will this type of place is the more warmer. So now from this LST map, we try to identify urbanite island zone. Suppose we try to find out this zone is the experience the higher temperature than their periphery zone, than their periphery zone. So this type of things, how we can easily monitor, we discuss about that. So let's go try to discuss about that. So if you check, we already know about the formula for Arvanite Island, LST minus average LST divided by standard deviation of LST. So this formula is simply compute. So when you compute this formula, I need average LST and standard deviation of two value I need. So let's go try to compute the average LST. So take a variable, suppose mean LST 1. So just I call the LST because I want to compute the mean LST from this map and apply here reduce region, compute the average LST from this map and put all of those. Just make a dictionary, curly bracket start and curly bracket end. So first of all, reducer. So I want to compute average EE dot reducer dot mean. Compute the average. Geometry, it's your shapefile variable name. This is ROI. Scale. Scale is the resolution of your satellite imagery, 30 meter. And others not need, just I remove. Not need. Now, just I print this mean LST. So print mean LST on the code. So now check the console tab. So this type of dictionary, it's average LST in this district, 25.88 degrees Celsius. But I need only for the value. So just use the same code. Just put the dot values and put the get from zero. But first item just on the. So now it show the average LST 25.88 degrees Celsius as a number. So I put here e dot number, because this number I also use further other equation or that I need to consider as a number computing. So now same way simply apply and compute the standard deviation of LST. Just I put suppose std LST and I put the function is std dev. Okay, and further I just copy the variable name and paste here. So now it computed the standard deviation of LST for my study area. Okay, so if you check the value is 1.51 degrees Celsius of standard deviation, okay, value. So now we generate the two value. We simply apply the formula, Arvanite Island formula. So take a variable USI and call this formula is, if you check, LST minus average LST. So LST minus average LST, basically it's the mean. We already compute, you can see mean LST, then divided by standard deviation, divided standard deviation LST. Just I copy and paste here. So now I just spread the layer of urban layer on the. So now if you check, it creates this type of map. So basically it's indicating urban heat island zone and non-urban heat island zone. So if you check this type of white color, it's indicating about the urban heat island zone. So urban island is a phenomenon where urban areas or cities become significantly warmer than surrounding rural areas. Okay. So if you check this type of surrounding area, black color, it has some vegetation or water body. So that's why this type of place not experience the higher temperature. And this type of white color, if you check this type of white color, it's indicating about that warmer, more warmer or significantly warmer, and mainly due to the human activities, to the presence of artificial surface, suppose concrete, it's artificial, or construction, roads, or settlement or household. So that's why it's create this type of artificial surface. Okay, so a climate effect in which urban regions experience the higher temperature than nearby rural areas because of buildings and roads, and reduce the vegetation. Okay, and also human activities, mainly concrete or buildings, road, it absorb and retain solar radiation. Okay, strong heat during the day and releasing it at night. Okay, so this type of artificial surface, it can be any artificial surface, suppose concrete, building, road, or others. This type of surface basically absorb and retain the solar radiation and storing the heat during the day and releasing it at night. Okay. So there's a lot of region behind on the Arvanite Island. Suppose cities usually have a fewer trees or grass or soil or water body, and vegetation cools the environment, okay, through evaporation. transpiration. So evapotranspiration is very important. It's because um, vegetation, this type of trees or grass, this type of vegetation cools the environment through the evapotranspiration. Evapotranspiration is one kind of process. So less vegetation means higher temperature. Suppose if there is no vegetation, then it higher the temperature. And a lot of human find out. Suppose vehicle, air condition, industries, then power plants. So this is called the anthropogenic heat. So in the city, anthropogenic heat increase day by day. And also urban geometry, it's very important because tall building, tall buildings create the urban canyons that trap the heat and reduce the wind flow in the urban. The air flow or wind flow it reduce, okay, and also prevent the cooling. So this type of causes it increasing the temperature, okay, this type of effect, and there are a lot of causes. So this is the main we easily find out. If you want, you can also use the different color. Suppose I just use the two color. Suppose I put the mean, basically two class, urbanite island and non-urbanite island. Okay. I put here suppose two color. I put here gray color. There is no effect of urbanite island, and that is for red. Just run the code. So now I can easily get the two gray and red. So gray is normal, only non-urbanite island, and red is urbanite island zone. We find out this type of map, okay, in the cities. So if you check this type of red color, it's indicating about the urbanite island zone. Type of red color, find out. And this type of place is the normal because due to the vegetation or trees or natural surface condition. So it's called the urbanite island map. You can generate, as well as if you want, you can also suppose you want to download this map urbanite island. So how I can download it as a GeoTIFF file? Same process. Just simply use the same line of code, then change the name, image name. Just put the USI, then it will also download it. Okay. So now we talk about the another. It's called the Urban Thermal Field Variance Index, UTFVI. FVI. So this Urban Thermal Field Variance Index, it's indicating the effect of urbanite island. Okay. Suppose where is the high effect, where is the low effect of urbanite island? It's called the UTFVI index. If you check, simply search, suppose urban thermal field variance index, you will search on the Google. So if you check, there's a lot of use index for the urban network. I also use to check some image. So if you check, they also give some values. So urban thermal field variance index value less than 0. Okay. Less than 0, it means that none. There is no effect of urbanite island. And ecological evaluation index excellent. If the value is negative, if the range 0.0002 to 0.005, then weak. Ecological evaluation index is good. Then you can see the normal, bad, odds, and odds. We find out that strongest effect. If the value greater than 0.020, it means that strongest effect of urban heat island. Okay, if the value 0.020, it means that. So now how I can compute this index? Okay, if you check the formula of this index is LST minus average LST divided by LST. So then we can get it. So let's go try to use it. So take a variable, suppose LST, sorry, suppose TFBI. I call the LST, subtract with, I already compute mean LST, and divided by So now run the code again. So map dot add layer, call the UTFVI and run the code. It create this type of map look like that if you check. So this type of place is okay. So let me just stressing look more better. Stressing suppose 98% I kept. How we if you want you can also add the color. Suppose just add the color. Suppose uh use suppose mean this is the negative 0.176. This value I just test x 0.19 and add the color plated and put here suppose blue, put here that green, so I put here yellow, red. Just run the code. So blue is indicating about the no urbanite island zone. Then it gradually increased, and red is the highest or strongest effect of urban heat island. Find out this type of map look like that. So this type of place is the strongest effect. Okay? Type of place. And if you check this type of place, or if you want, suppose I want to identify um, from this type of excellent and strongest or worst ecological evaluation I to identify. How I can identify this type of place, excellent place, so worst place. So then we simply the value less than 0.0 or less than 0, and you can say that it's excellent ecological evaluation. So let's go try to show you how to do it. So just I take a variable excellent ecology. You can put anything, no problem. And now I just call the UTFVI, then put here that less than 0.00 something this value. So now at the map layer of excellent ecological evaluation players on the code.